Emulsions are colloids made up of a liquid dispersed in another liquid. And we can divide emulsions into two categories. We could have macroemulsions and microemulsions. The difference between these two is that macroemulsions are inherently unstable. And what happens with a macroemulsion, so a macroemulsion is made up of fairly big droplets of one liquid dispersed in another, is that we're going to get some kind of separation of the two phases. So we're either going to get creaming, where the dispersed phase is less dense than the continuous phase. So an example of this would be cream. So you have whole milk, and the fat is less dense than the water, and so it rises to the surface. And once that happens, we could have creaming, or we could have settling if the dispersed phase is more dense than the continuous phase. In either case, we're going to end up with a lot of dispersed phase right next to each other. And once that happens, the droplets start to adhere to each other. In other words, we have coagulation. And beyond that, because these are liquids, once the particles are attached to each other through a dispersion interaction, the droplets can actually coalesce. The boundary between the droplets disappears, and eventually we have just one droplet. And that can happen. All the droplets can merge into a single layer. So we call this coalescence. So basically the emulsion's completely dead at that point. We just have two layers. So if you've ever used a separatory funnel to separate the organic layer from the water layer, you shake the funnel and you usually get some kind of macroemulsion. But very quickly, the less dense phase gathers at the top and the droplets start to coalesce into a single layer. Okay, and this is something that happens when we try to mix two phases that are sort of dispersed, one phase and another, and they're insoluble in one another. So if we just have two components, we'll invariably get a macroemulsion. So oil and water, or hexane and water, or something like that. Well, microemulsion's different. A microemulsion is going to be stable. And the reason it's stable is that we have some third compound, which will be some form of emulsifying agent. And that third component is going to be able to keep the emulsion stable. We can imagine making an emulsion where we have droplets of water suspended in oil, and we would just call this a water and oil emulsion. We could also imagine a situation where we have drops of oil, meaning anything that's hydrophobic, suspended in water, and we would call this an oil and water emulsion. And finally, you can also have nested emulsions, where you have droplets of a phase. For instance, we could have water in oil. So we have these big droplets of water. And then within those, we could have additional droplets of oil. So in this case, this one would be a oil and water and oil nested emulsion. So what stabilizes microemulsions? Well, we need some form of emulsifying agent. And most typically, this is a surfactant. And when this sticks to the surface between the two phases, the interface between the phase, it can stabilize the emulsion in a couple different ways. So let's imagine that we have an oil droplet, and we take a surfactant and stick it, just put it into the emulsion. Well, we know if we have a oil and water emulsion here, we know the surfactant would stick its polar head group into the water and the tail into the oil. And that's going to do a couple of things. First of all, it's going to decrease the surface tension. So that means this interface is no longer as high in energy, and that reduces the driving force to getting rid of all this surface area that we have when we have this phase dispersed into many small, dispersed into many small particles. Second, if we have a charged surfactant, so imagine that we had SDS or some other anionic, or indeed we could do this with a cationic surfactant, that means that if I have a second microemulsion particle over here, we can see what's going to happen. We're going to get electrostatic repulsion, and that's going to keep these droplets from getting near each other. And finally, we can imagine putting on using a polymeric emulsifying agent, and then we could have steric stabilization, as we saw when we did the stability of solid colloid particles. The ideal surfactant shape for a given emulsion is going to depend on the curvature. So imagine we have an oil. Let's do a water and oil emulsions. We've got a water and oil emulsion, so we've got our water here, and it's surrounded by oil. We want to stabilize this. We can see by the curvature we want to have a surfactant that's going to take up a lot of space in here and not so much here. So the curvature of the surfactant layer adhering to that interface will match the curvature of the interface. So I might want to have a surfactant that had a lot of nonpolar tails and a relatively small head group. So we can see how that would stabilize that interface. On the other hand, if I wanted to do an oil and water microemulsion, in this case, so I've got some oil here, some water out here, we can see that I want to have something that's bigger on this side. So on this side I might have something with a relatively big head group and maybe just a single chain or a smaller tail. And we can see this sort of matches what we saw when we did surfactant number, that the shape of the surfactant affects the curvature that it will adopt. And in this case, we use a different parameter though. Since we're not talking about just a micelle, we're talking about a droplet where these are just in the layer. So this is not really drawn to scale. This oil droplet might have a radius that's many times the length of this tail. So the parameter we will use, the HLB, or hydrophile lipobalance, will be discussed in the next screencast.